Right, so welcome everyone to today's webinar, which is also the launch of this Tools4DS webinar series. And this is championed by the early career researchers, part of the DSI community. So our first presenter for this webinar series today is from the University of Cape Town, here where I'm also based. So I'm happy to introduce Christiana Kinde, who's volunteered to go up first. So a little more of the webinar series. We thought to put together a showcase of tools and resources or applications that is part and parcel of data science and can be used also for health innovations. So we wanted, drawing on the resources and talents of the DSI Africa community, to showcase these tools for us as part of a webinar series. So we're hoping to have this webinars take place at least every second month, so it's not too much. And we hope to have at least 1 to 2 speakers at any given webinar. However, if you have any more ideas or would like a guest presenter from outside of the network, please let me know via email. Or if you feel that there's a need in showcasing a tool, then you can also let me know via email, and then we can see if we can make it happen. All right, but without further ado, I will hand over to welcome Christiana today to take us through some tools regarding identifying cancer driver genes. Thanks, Christiana. Over to you.
Okay. Thank you very much for the kind introduction, and I'm also very grateful for this privilege, and I'm hopeful that it's really going to be a time worth it. Once again, my name is Christina, and I'm a PhD student at the CO BIP division. Yeah, so it's a new program, basically involving data science analysis in cancer genes at the moment, but I know there will be more projections with time. So this afternoon we'll be discussing a very important tool, very important in the sense that it's very relevant to the current findings in cancer research, and that is OncodriveCLUSTL. Okay, so I'm just going to briefly go through the outline of the presentation. The first thing we'll be doing is to look at the implication of mutation clusters in cancer genes, because the tool basically is to identify mutation clusters, and then after the identification of mutation cluster, to see how that driver genes can be extracted from the identified mutation clusters. Yeah. So we'll be looking at that as a foundational discussion before we go into the, the running of the tool itself. Then I would also discuss what OncodriveCLUSTL is, the use and the algorithm behind it. I would also compare the present tool with the previous one, so we can, have an understanding of the advantages, the relevance, and the application in recent findings. Then the fourth thing we'll be discussing is the installation and the implementation of the tool, for as many people would also, implement the tool going forward in their research topics. So the fifth thing we'll be doing is to look at the input and the output files. So for the tools, it's very important to have, a good input file that is well arranged, the required, data is being imputed, and every necessary thing, because if that is not done, it's possible to start getting errors, which can be very frustrating, Yeah, so the last thing we'll be doing is to run an example on the tool. So I know that we might not be able to, capture the whole running procedure, because the simulation time takes about 30 to 2 hours, depending on the size of the file, but they would go around it and see how we can work within the limited time. I've actually run an example, so we can start, and I'll show you the output files, and the implication of some of the files, how to interpret the results and all. Okay, so when we talk about mutation clusters, we all have an idea of what, okay, I don't want to assume everyone, so I'll try and, bring everyone to the same page. Cancer itself is one of the most dangerous diseases because it poses a threat on the public health. It's actually the second reported disease, globally. So the genes carrying mutations are actually very critical for the establishment and development of cancer. Why? Because when we talk about mutation, it's an alteration. It's an alteration that happens during tumorigenesis. That is the progression or the transition between normal cells to cancer cells. Okay, so now it becomes, very important to study the pattern of tumor mutation and how effective it can be in the identification of cancer genes. So this is actually done, by studying the pattern of tumor along the protein sequence, and it has over time helped in the identification of cancer drivers and also gives clues to oncogenic mechanism. So one of these signals is the abnormal clustering of the mutation. The alteration we're talking about gives a signal, and this is attributed to the abnormal clustering of the mutation. So it's a way of complementary other, patterns or other functional ways of identifying driver genes. So reports have actually shown that the rate of mutation generation across the genome is highly variable. It changes with time. So there's need for a clustering-based method that's capable of constructing an accurate background model of the distribution of mutation to correctly assess the significance of observed clusters. So that is where the OncodriveCLUSTL comes into play. So it's actually a tool that helps to identify the clustered mutation, because if something is scattered, it might be difficult to actually pick out significant driver genes. So there is need for a tool that would be able to identify the cluster mutation and also bring out the significant driver genes in it. Okay, so OncodriveCLUSTL comes to bring solution to that, and we'll dive straight into it. So what is OncodriveCLUSTL? So it's actually a new linear clustering algorithm to detect genomic regions and elements with significant clustering. So it identifies mutation clusters in human promoter regions. And the interesting thing is that it's not limited only to the human genes. It also helps it can be used to identify cancer genes, in non-human data and also in non-coding regions. So it identifies cancer genes in coding regions, in non-coding regions, and non-human data, which is, a plus to it, like an advancement, as we're still going to see when compared to the previous two, in the sense that this has the capacity that it's even beyond the human data. For example, maybe for some data that the human samples are not available, maybe for those who are working in vivo, So it also analyzes somatic mutation that have been observed in genomic elements across a cohort of tumor samples. Like I've said, it identified mutation clustered and driver genes across the cancer genome atlas cohort. So quickly, I'm going to compare the difference between OncodriveCLUSTL and the previous one, which is OncodriveCLUSTL. So the difference now is the L. The additional, word in the name is just the L, but there are actually a lot of development in the previous one and the recent one. So the previous one is it actually outperforms the previous one that was developed from protein clustering method. And the OncodriveCLUSTL, which is a previous tool, is obtained from a background model from synonymous mutation in both the true and false positive rate. And it has several weaknesses in the sense that sometimes, one of the weaknesses that it disregards drivers whose mutations are distributed across the sequence. And then for it to be able to bring out significant driver genes, it requires a large quantity of observed mutation in order to ensure a good outcome. However, the current tool, which is the OncodriveCLUSTL, has actually helped to solve, several of these weaknesses. And then OncodriveCLUSTL also exhibits similar specificity and sensitivity as a 3D protein clustering method for the hot maps. So it can identify cluster of truncating or silent mutations. Sometimes it's easy to ignore some of the seemingly not significant or non-synonymous mutation. But the truth is that some of those types of mutation could actually bet significant cancer driver genes. So this tool is capable, of identifying clusters in the truncating or silent mutations. In addition, the result of OncodriveCLUSTL complements other methods, that are based on distinct signals of positive selection. Yeah, so we'll move now to the installation and implementation of the tool. So, okay, let me just raise a disclaimer at this time that I'm not the developer of the tool, but it's a tool that was actually a previous step that that I underwent in my current research procedure. Thankfully, my supervisor was able to, identify the tool, and it's been quite helpful. So graciously permitted me to share with the ECHOW DSI Africa group, and I hope it's going to be useful for others as well. So it's so in that sense, I'm going to send the link that explains more on the installation, especially the major steps that should be taken, but I'll just give a brief summary of it now in the presentation. So the OncodriveCLUSTL depends on Python 3.5 and some external libraries. So it's mostly recommended to use the Anaconda Python distribution for the installation. So there is a particular command that needs to be imputed into the terminal, for the installation. One could use either the conda or the pipe to install it on the terminal. I didn't put the slide here, the command here, because I'm still going to, the links have been attached to the slides, and I can also put it up at the end of the presentation. So the next thing is the input file for the data. We're going to see that now because we'll be running an example on the tool very quickly. But it's important to take note that the arrangement of the input file in terms of it containing the required, data is very important to get the good outcome that is needed. So basically, there are two main input files, and that is the mutation file and the annotation file. So the mutation file, okay, let me just say here that both files, they must be imputed first as a tab separated values, not in any other format. If not, it's going to give a lot of errors, and just that little step would actually cause unnecessary frustration. So please, that should be noted, and the input files should be zipped. Yeah, so you can perhaps zip it on your terminal before you run the tool, or any other way that works well for you. So the mutation file is actually, a substitution file, nucleotide variant substitution file that is mapped to a reference genome. So for example, maybe the human HG1938, depending on the one you want to work with. So if you're working with non-human gene, you could use maybe mouse C3H as the case may be. So the mutation file can actually be downloaded from the cancer databases. So another thing I would love to point out is that the annotation file and the mutation file must have similar reference genome. For example, if you're using a database with AG38 for your mutation file, then the annotation file should also have the same. Okay, so you don't have to download maybe AG37, it has to have the same reference genome. So for the mutation file, you could download it from cancer databases such as Xena. Yeah, so depending on the type of cancer you're working with, but most of those cancer types, they have, the mutation file attached to it. So when you have the mutation file, you can now, filter out and select the required data from the big mutation data that you've downloaded from the databases. We're still going to see those required part of the mutation file that is needed for this tool. Yeah, so for the annotation file, so the annotation file also contains a CSV file, very important, and it should be zipped too. But it contains the coordinates of the genomic elements, which implies that it can be downloaded from genome browsers. Yeah, so and there are basic things that should be imputed in the input data. So primarily, there are about 5 basic columns that should be present in both the mutation file and the annotation file, although there could be some addition depending on your research focus. Yeah, so I'm going to just read out the basic columns that should be present in the input file. The first is the chromosome. I'm going to show us an example of what I mean, but the chromosome column should be there, yeah, with the, the type of chromosome. And, a number of genome browser could record chromosome as CHR1, 2. So one of the errors you want to avoid is also to ensure that you don't include the CHR1 or the CHR2 or the CHRX and Y. You want to remove all of that to ensure that it's just the chromosome name itself that is included. Okay, I'm going to show us an example to explain that better. Then the mutation file should have the position, that is the integer that indicate the position of the mutation, then the reference nucleotide, the alternate nucleotide, the sample, that is the identifier of the sample, then the ID. So the ID is more like an ordered numbering of your input sample. So my supervisor and I actually wrote a script, a simple script to do that. So, and when you see the example file, you would understand what I mean. Okay, so other additional columns could include the cancer type. Yeah, maybe you're writing an article and you want to put that just to ensure everything is in order. You can also include that as an additional column, and also the signature. So for the annotation 5, the 5 important columns that should be in your input data is your chromosome, your start, which is the starting position of the genomic, region, then the end, which is the final position of the genomic region, the element, which is the identifier of the genomic element, then the symbol of the genomic element. Yes. Then you can also include the strand, yes, which is an additional column. So this is an example of a mutation file showing the chromosome, the position, the ref, the alternate, the sample. Those are the 5 basic columns that should be present in the mutation input file. Then the annotation file, the chromosome, the star, the end, the strand, and the element ID. Okay, so the output files, at the end of the day, after you've run you've imputed your data and you've actually done the simulation on it. So what are the expected files that you should have? I mean, that would actually give you the results you require. So the first is the element results file. So it's also a CSV file containing results of the analyzed element, and it contains symbol, the genomic, element ID, the chromosome, major things, but I'm just going to lay emphasis on few things. It gives the score of the genomic element and the P empirical value, which is a P value because you need all of that in the interpretation of your results. The total mutation, the clustered mutation, that is the number of mutation in the cluster. And the next file that one would have after the simulation of the two is the clusters results file. So it has the rank of the genomic element. It gives it as, the position based on how important the cancer driver gene could be. Yeah, so the symbol, the chromosome, the strand, and the score, which is a cluster score, then the p-value, which is the analytical p-value of the cluster. Those are very important, details in interpreting the importance of the cancer driver genes. So we're going to run an example quickly. Okay, sorry, the last output file is the log file. Basically what this does is it gives you the progress of your simulation. So for example, you've imputed your input file, you want to know how far your work has gone, you can just check this file, because as soon as you start running the tool, it's going to create an output file that you can check the progress of your work to see everything is still intact. Yeah, so to run the tool, the first thing is, I think I would love to demonstrate that now. Yeah, so I'll stop sharing my screen and use I actually installed the software on another system, not this. But the basic thing is you need to open your terminal with the directory of the file, then write the command for the simulation. Also ensure to indicate, I'm going to show us that, to indicate the result folder in the command line and keep checking the progress of your simulation. So let's quickly run an example. Like I mentioned earlier, we might not be able to wait for the results, but I've done that already. So I'm just going to show us the results, the example, and yeah. So let me know if you can see my screen at any time. Please let me know.
Not yet, Christiana. I think yes, Christiana.
Yes, I am. Please kindly give me a minute. I'm trying to sort out the technicality of the other system.
Sure.
Yeah.
Sure. But in the meantime, folks can gather their thoughts and note down questions for Christiana at the
everyone. Am I audible now, please? Okay.
There's a bit of feedback from your side,
Okay.
but we can see your screen.
All right. I'm sorry about that. So I'm just about to run an example of everything we've discussed so far in terms of the input data and the command, the terminal, and yeah. So let's see what happens. Okay. So this is an example of the input file. So let's just see how it looks. So this is the mutation file, like I explained earlier, the chromosome, the position, the level. This is for a particular cancer type, the alternate gene, input rather than the sample, the ID. So like I explained earlier, this is actually very important because it helps in the iteration of the simulation. So it depends on the total number of your genes. Yeah, so you can just write a simple script to ensure that the numbers are well assigned. Yeah, so that is the mutation file. Then the annotation file. So like I said previously, it depends on what exactly you're using. So for this particular simulation, I used the EGS38 because the reference genome for my mutation file is EGS38. So I'm going to show us that as well. Yeah, so it has a chromosome, the start, the end, the strand, the element ID, transcript ID, and the symbol. Try and ensure that the arrangement of the column is the same as the example. Yeah, like I said, I will send in the example link to us so that we align our input file in that order. Yeah, so that being said, I'm just going to open the folder in the terminal. So my input file, okay. My input file and both input files now, the mutation file, the annotation file, both here. Like I mentioned earlier, ensure that it's in the tab separated value, and the input files must be zipped. So I've already done that. So I actually have a number of them that I run because I'm working with different subtypes. So I'm just going to use one of the mutation file. Yeah. So I'm using this. I saved my mutation file as the subtype 3M final. And you have to indicate the output folder. That's very important. Okay, let me just explain here that the AG38 is the annotation file, which I've explained earlier. So the command instructs that the imputed annotation file and the mutation file should be simulated, and the results file should be stored in HALT3. So for example, here, I'm just going to change this to 7 because I've actually used the HALT3 for other simulations I've done so that there won't be repetition. So I'm just going to change it to 7 to form a different folder. Yeah, but basically this command is also in the link. So you can just, copy it and then change the command to indicate your own file name. Yeah, so when the simulation starts, it shows you the number of mutation. Yeah, then the number of restricted regions and some of the cluster mutations that have been recognized. Yeah, so we might not be able to wait for this because of our time. So I'm just going to show us the output file, then we'll discuss on that and give room for questions. So maybe I should just wait a little to make us see how it runs. The simulation time differs depending on the size of the data, and I think other factors might also be attributed, like perhaps the processor of your laptop, yeah, and maybe the workload, because sometimes, let's say it takes an average of 30 minutes to 2 hours. Yes, putting all of those factors into consideration. So like I explained earlier, you can actually keep checking the progress of your work. Remember, we named our output file as 7. So you can go back to your folder. So you can see the passport folder that was indicated, so it's already included here. You can check how your result is progressing. I mean, your simulation is progressing. Don't know what's happening. It's not opening yet. Yeah, okay, cool. Because I'm using the same system for the presentation, it's taking a while. So yeah, so the results log actually gives the progress of the simulation, because sometimes you want to be sure you're still on the right track. Okay, so it's showing that it's gone 2 out of 8 simulation. Then it's also giving some information about the number of elements mutation. Yeah. The validated element with mutation, the validated element in genomic region. So even as the simulation is ongoing, you can still get, have an idea of some of the output file results. Yeah. So basically at the end of it all, what you have is this. So these are other input files that I've actually run before now. So I'm just going to use one of them as an example because we might not be able to wait for this. So at the end of the day, when it's over, it's going to write finished. And you can also, check that in the log file to ensure that the simulation is over, like it's ended rather. So this has, I think, 8 iterations because the input data is very small. For some, it could be 21 or more, depending on the size of your data. So at the end of the day, when it's completed, you have this 4 output data, like I've explained earlier. So the cluster results is a very important output file. Just gonna open it now. Okay, so it gives the symbol of the mutation driver genes and some other information, the chromosome, the strand, the coordinates, as well as the score and the p-value. So the p-value gives an indication of how important the G file is. And like I mentioned earlier, it arranges the symbol, it ranks them in order of importance. So for example, it's the TBCID2B is showing high importance. And if you check the p-value, it's also, relatively small. Yeah, but if you use other data, you could get a better result. But for this, the p-value is 0.04. You could get of lesser values, with more importance. So in essence, the cluster results gives an indication of the importance of the identified driver genes. So all of these genes, they're showing their indication of the mutated genes, that are indicative of driver genes in cancer. Yeah. So to get more information on some of these genes, you can also check the other output files. So I'm going to just open the remaining 2 now. So the element results gives more information specifically for all of those identified genomic elements. So it gives length, the total mutation, the clustered mutation, the clusters, the sim clusters, the score, P empirical, the Q empirical, the P analytical value. Yeah, which are, factors to be considered in how important the driver genes are and in the interpretation of the result. And it also gives a plot that shows the identified genes in order of their ranking, in order of their importance. Yeah. So I think I would like to stop here for questions. And I'm going to stop presenting on this side and share the previous screen that has the links. So I've actually imputed some helpful links, the example links, that has the command line and other information. Yeah, articles, here in the slide. So if you need more details, you can just check it out. I also added my email address if perhaps you need assistance at any point in time in running the steps. I'll be more than happy to be able. Okay, so I'm So grateful for this privilege to present once again. Yeah, and I'm very grateful to my supervisor, Dr. Osin Bendal. Thank you so much for your excellent supervision. I don't know if he's here, but he actually permitted me to do this presentation. Then my other colleagues, NASA, Michelle, thank you. It's really been great working with you. I think Michelle is here. Then I'm also grateful to my founders and promoters, Professor Nicola and Prof. Tinash. Thank you very much for your time. I wouldn't know if there are questions. These are references to my presentation.
Thanks so much, Christiana. There's a few questions in the chat. I can just read them for you. Or I'll read them out, but you can have a look as well. So Michelle's asking, you mentioned there's a small input data set. What is the size of that input data set when you were running the analysis in the demo? Christiana, you're muted if you're talking or something. Christiana, are you there?
Yeah, please, can you hear me now?
Yes, we can hear you.
Okay, yeah. So when we talk about the size of the file, I was actually referring to the number of tumor samples you have. So for example, if you're working with lung cancer, you check the data base and you realize that you might not have the same number of tumor samples as other types of, cancer type. So it depends on the number of tumor samples that you have. Yeah, so for example, the imputed file that I used, I just included about 12 tumor samples, which is actually very small. Yeah, it's relatively small. But the good thing about the tool is that it takes all types of mutation and then brings out the significant one. So even if the mutation number is not as large as it ought to, so the advancement in this tool is that it will still run the simulation, discard the non-significant ones, and pick up the significant ones. Yeah. So I don't know if I've been able to answer your question. So I'll just go to the next one. It says, do you plan to make this tool in user-friendly using? So like I said earlier, I raised the disclaimer that I'm not the developer of this tool. So I guess that question would be to the developer. I just found it useful in the course of my research, and I thought to share, yeah. So the next says possible to the whole genome sequences. So we just have to target some necessary chromosomes. Yeah, it's actually, remember that the reference genome, it's the human gene itself, yeah, that you've downloaded from the genome browser, depending on the specific one you're using. I use Ensemble. So if you've downloaded the genome reference, it's more like, the whole gene, the whole human gene is there. And needful to mention is that you can actually use it for not just the human gene, you can use it for, perhaps non-human gene, and it can also be used for non-coding regions. Yeah. Okay, so the next one says, thank you for the presentation. Can the tool do visualization of the results? Apparently, the output file shows the visualized outcome, and that is the plot. That is one of the output files gotten. Like I mentioned, we have 3 output files. The one that gives an indication of the cluster mutation, then the the element of the genomic element result, and then the third one gives the plot of the selected driver genes. Yeah. Yeah, I can't see any other question here again. I wouldn't know if you have any on your side, Rolando. Sorry, I'm not sure I'm pronouncing the name well. Permits me.
No problem.
Okay.
No problem, Christiana. I don't have any questions from my side. I don't. Maybe just a general question. So if this tool, besides you testing this tool, do you know of any other projects that have implemented this tool in other cancer research?
Yes, yes. Actually, the first example that was reported is not on the type of cancer type I did. I'm working on colon cancer. So it's actually been implemented on other colon cancer, other types of cancer. Yeah, I think the initial one was on lung cancer. Yeah. So it can be used for the different types of driver cancers, different types of cancer rather. Yeah. So I also see a question from additional on, can the tool directly take a VCF file? Yes. Yes. So if you check the example link I attached to the slide, maybe I'm just going to also put it up on the chat box. So the command line you used for VCF file is different. So it's also been modified such that if you have a VCF file, you just, kind of modify the input command line in your terminal. Yeah, but you can use a VCF file. Yeah. Thank you for the question. Can the tool be used for malaria data set? Well, I think perhaps it depends on your research focus. Yeah, so what area of what is the research question you're trying to answer? Because basically the use of the tool is to identify cluster mutation. So if you're looking for that in malaria data set, as you mentioned, I think it can be applicable because like I rightly mentioned, it's not just for human data alone, it can actually work on non-human data. And I think the causative agent for malaria, Anopheles mosquito, falls in that category. Yeah. Okay, so how do you interpret your result? Supposing you need to disseminate. Sorry, am I supposed to read out the question? Apologies, Rolanda.
That's fine.
I'm not. All right. Okay.
No, that's fine. Go ahead.
So I'm actually using a bigger screen here, so it makes it so easy. So how do you interpret your results, supposing you need to disseminate your findings to non-technical people who may not know much about cancer? Yeah, that's a good question. And, that is why I actually started the discussion with what cancer is, the importance, the application of the mutation clustering and its relationship with driver cancer. Yeah, so at the end of the day, when you have your results, you have a list of mutation clusters. So from the list of the mutation cluster, you want to identify significant mutation that infer or, predict driver cancer genes. So when we talk about driver cancer genes, they are modified normal cells that have become cancerous due to now mutation. There are different alterations that could actually happen to a cancer gene. Yeah. So, breaking it down to say, okay, these genes, they are the mutated genes now as a cluster, giving a signal for cancer driver genes. Yeah, so the p-value, it's also an indication of the ranking or the importance of the driver cancer genes. Yeah. Oh, absolutely. So the spreadsheet for the tool, yeah, I think all of this information can be extracted from the link. Yeah, so it's actually well, outlined. You're going to get the I'm not sure if you get the limitations, but definitely the input file type, the output file type can be there. But yeah, but I mean, if we're not out with help, that's okay. Right.
Sure.
But I feel everything you need is in the link, yeah. But if you need assistance, it's okay. Yeah.
Thanks, Christian. I don't know if there's any more questions.
Yeah.
All right, then I'm gonna call this day for this webinar. Thank you so much for everybody that attended today, and thank you also, Christiana, for being the first one to volunteer your providing your skills here on presenting this tool to us. We hope this is the start of many more of this type of webinars to come, and we hope to see you presenting in this tool to more conferences and symposiums. Right, thanks everyone.
I'll be glad to do that. Thank you.
Thanks, have a good day further.
Yeah, bye everyone.
Bye. Oh, so yeah, let me just, we mentioned we will upload the recording to the DSI Africa YouTube channel. And if Christiana permits, we will also upload her slide deck. Right. Thanks everyone. Bye.